Hello, my name is Murray Estes. This is my presentation for Lab 2 Stack Buffer Overflow for CS428. The purpose of this lab is to show how buffer overflow happens and to demonstrate some of the defenses we have against such an attack. First, what is buffer overflow? This happens when input into a buffer exceeds the length of the buffer, overriding other information that is adjacent to the buffer in memory. Normally this occurs when the buffer input is not checked prior to being used, and this could happen for many reasons. For example, it takes time to check every single buffer. If you want a fast program, you may not always want to check the buffer. And so you enhance your runtime speed at the cost of security. Or maybe there's just so many buffers. You just happen to overlook one. Of course, there's languages that do this to check this input for you and will not allow buffer overflow, such as Java. And maybe whenever you have a lot of buffers, maybe you should use this language. And then, of course, the experience of the programmer comes into play. The new programmer may just not think to check about the buffer. And this is why we have code review. It is always a good practice to have other programmers check out your code. They'll see things that you don't. And likewise, you will see things that they don't in their code. And these vulnerable buffers are an attack surface for a potential attacker. They will use this buffer to inject bad code into the system. In particular, they will try to override a return address with the address of their code. This is not necessarily an easy thing to do, but maybe they can get close enough to where the system finds their code anyway. And this becomes especially problematic when the program with this vulnerability has root access. The entire system is then at risk. What are our defenses against buffer overflow? Well, there's good coding practice, coding defensively, checking your buffers, and all that good stuff. And you have address randomization. This randomizes the address for your program, and it can make an attacker have to guess where the return address many thousands of times if done correctly. Or if the attacker maybe is less skilled. If he's more skilled, then this is moot. There are algorithms that detect abnormal stack behavior, and Linux uses something known as stack guard to do this. It warns the user of an attempt to access the stack, and then terminates the stack. Other modern systems will have similar systems to this. And then there's making the stack non-executable. This is a fairly recent thing, only since the early 2000s, if I remember correctly. But this is now default behavior for modern compilers, and it prevents code that is on the stack from being run. Now we get to the lab itself. For this lab, we were provided with 3 pieces of code: stack.c, exploit.c, and callshellcode.c. Call shellcode was just for a demonstration of what the shellcode would look like should we successfully write exploit.c. And so for each task, we were to write exploit.c in such a way that it would call a shellcode using buffer overflow. As that's in task 1, this is the most time-consuming of all tasks, because not only do we have to modify that exploit.c, we also have to initially compile stack.c to run with root access. We then have to find all the information we need to find about the return address and the size of our shellcode and where in the buffer should we put it. All of this we do in task 1. So for this, I use bad file, which is a part of which is a file that stack.c calls for input into its buffer. I use this to kind of probe where the return address was. In this initial image here, I've filled bad file with 24 A's, 24 being the size of the buffer. I use this so I can find what's the address of the particular function that calls the code, which in this case is string copy. And at the code I have highlighted, or the address I have highlighted, I set a breakpoint. I need this so I can examine what's going on at that breakpoint. So in particular, I want to see where the buffer itself actually lies in the address of it. And we can see here it begins somewhere between Bravo Fox 140 and 148. So I should return somewhere between those two. I don't want to return directly at the beginning because some randomization does occur even without address randomization enabled. So I want to advance a few spots ahead of where the buffer begins. So now I expand my input until I can see, until I get a seg fault, and I had 4 more A's in this case. So I can recognize where it's trying to return to. In this case, it should be 61616161. I run the GDB debugger, and what do you know? 61616161. We have our 4 A's for the return address. Now I have one more thing I need to do just to verify that I've got my location correct. I changed the A's with B's, which is hexadecimal 62. Now the address should be 62626262. Do this again and again. We see we have found where our return address is. This confirms where I thought it was. So now I have almost everything that I need. Not quite all, like I said up there, because I need to now know the size of my shell code, which I determined to be 24. So because the return address begins after position 36, I need to put shellcode at 36 minus 24, which is 12. And everything before that is going to be NLPs, non-operations, and that's hexadecimal 90. And you see that I have my address written backwards, and that's a feature of modern systems. This is known as Little Indian encoding, which is used by modern hardware. And there's the shellcode, which was part of exploit.c, and I determined it to be 24 bytes. And now we actually get to run the code. And for this, I need to ensure that address randomization is disabled, that the stack protection is disabled, and that the stack is executable. And so we run it. Just go from the top. I make sure I'm in root access so I can disable address randomization. Then compile stack.c to where the stack is executable and the stack protection is disabled. And then I give it root access with chmod. Then I run exploit to generate the bad file. I run stack to read from the bad file. And now I have a shellcode. We go into test 2. Where the only thing different between test 1 is we enable address randomization. Yes, I did take address randomization into account when I modified exploit.c. Hence why I made the buffer, the return address, a few places beyond where the buffer began, just to take into consideration for when the address is randomized. Because we see I do not recompile stack.c because address randomization is system related. It has nothing to do with the code. So recompiling would have no effect. And for the record, I actually did recompile it. I initially did the lab and it had no effect. This was what I got the first time. I ran test 2. So you see I re-enabled address randomization, and then I ran call exploit. I no longer really need to call exploit at this point as I'm not changing the bad file. And then ran stack, and we get a shellcode. That was always the case. Even as I said, when I did recompile it, when I initially ran the lab, I got no change in effort no matter how many times I ran stack. I never didn't get the shellcode. So for test 3, we again disable address randomization. This is just to show that address randomization isn't potentially causing the problem, and then we enable the stack protection, which is recompiling stack with that tag. And we see we have done this, and we get a nice little notification, stack smashing detected. And then the stack is terminated. And then the seg fault because there's no return address. Segmentation of fault occurs when your return address returns you somewhere into a bad segment. In this case, there is no return address, so you're in a bad segment to begin with, and that system sends a fault and terminates the process. The final task of this lab, we disable stack protection, but now we make the stack non-executable. And this should just cause us to go into a segmentation fault because we're returning to a bad segment. And lo and behold, we have a segmentation fault. The way to get around these two would be to instead try to either go into the heap or go into dynamic memory, but that's beyond this lab, so no attempt was made to do that. And this concludes my lab. I thank you, and I hope you have a good day.